So most of the time, I'm probably going to be uploading things to the Google Classroom page. Now, I don't know if everyone is a member of the Google Classroom yet. So what I'm going to do is I'm going to put this code, right? SFBSJ2V on Compass so that everyone can go on to Compass and then get that. The reason for this is that I'm going to be uploading, I'll try and upload things on both of them so that, you know, if you don't want to look at the other one, but there will be some like worksheets and things and quizzes that I will upload directly onto here. So I've got most people here. And I think actually, yeah. So some people will have seen this pop up as something that they need to do, but I put this link, this scheduled Zoom also on Compass. Now I want to show you this. Now, this is not our class, okay? This is for my science class, but what I'm going to be doing is I'm going to be creating, hold on. Sorry, some people have just joined. What I'm going to be doing is I'm going to be creating a page similar to this for our class. Okay, it will be year 10. It'll be essentially year 10 engineering, and it will just have week 1, and it will have a list of all the things that I want you guys to do. I haven't made that yet for this class, and that's because I've just been trying to get all my other subjects ready, but I will make one of those things. This would normally be a single period anyway, so I'm not going to go through too much. What I think I will do though is I will, the other thing I'm going to be doing with you guys is I'm going to be uploading the PowerPoint. Can you guys see this window at the moment with the PowerPoint?
No.
No. We only see Google Chrome.
Oh, okay. All right, hold on a sec. Let me see if I can. Let's see if I can jump over here. Okay, can you see it now?
No. Okay.
Yeah, it's there now.
All right, cool. What I'm thinking about doing, by the way, hey, Jess, cool. The one more thing I'm going to do. Actually, let me just stop sharing for a second. Considering I've got a fair few of you guys in the classroom now, can I get you guys to do me a favor? Could you go to the chat function? And all I want you to do in the chat function, which should be on the right hand side of the screen, but I'm not sure, it depends. I just want you to click on, I just want you to type, I'm here, I'm present. Because what I'm going to do is I'm going to actually cut that piece of chat out, put it into a document, because later on I have to do the attendance for this class. So I have to say who was here, who was not here, and so on and so forth. And so then I can just quickly get everyone's names and I can quickly put them in. Okay, so cool, beautiful. For those of you that just joined, tried to use Google Meet this morning and it was okay, but it was a bit, I couldn't mute people and I couldn't organize things as well. I find that Zoom has a lot more functions in it, so I may be using Zoom. By the way, Min, when you write down you're attending, can you also tell me which Min you are? Because I have 2 Mins and there is like, yeah. But that should be good. Oh wait, no, both Mins are here anyway, it doesn't matter. Okay, so what I'm going to do is I'm going to attempt to go through this lesson as I would normally go through it anyway. if I go, can you guys still see the screen?
Yep.
Okay, is it really big? Does it take up the whole screen or not?
It takes up the whole screen.
Cool.
Yep.
Excellent. Thank you for that. All right. Yeah, I might go through this now, and I'll just sort of I'm not going to mute everyone. I'm going to let you guys be like that. If people start talking a bit too much, then I'll just mute everyone. What I'm going to talk to you guys about now is this is the lesson. I'm going to go through this first little bit briefly, and this is just going to be a very, very short lesson. This is a bit of a trial run, if you will. And then I'm going to give you guys, what I've got for you guys to do is later on, not now, but later on after this lesson, we're going to work on Electronics 1. And I'm going to give you guys that as homework as part of this Google Sheet. I'm going to talk about that probably tomorrow. So tomorrow I might do another mini Zoom thing, and we'll see how we go. But that's going to be the homework, but I haven't given it to you yet. So all I want you to do today is just to listen to the main ideas for this session. So
No homework today.
No homework today. Just focusing on this today. So just this.
Sicko mode.
So
you still have
What?
So do you have our books?
I
Yeah,
do
you still
have
have
most of your books. So what I can do.
Oh no.
So what I can do with your books is I can maybe put them at the school somewhere. I might be able to like give them to the office and then they can hand it out or something like that. But otherwise you might just have to write it on loose leaf paper or something like that. It's a bit unfortunate because I wanted to give them back to you obviously the last week of school, but it just didn't work.
Can we just
Okay.
start a new book?
Or you can just get a new book.
That's a good idea.
Yeah, let's have a look at this guy here. So we're looking at lesson 11, and it's lesson 11, current and voltage. So the idea that I wanted to quickly talk to you guys today is I wanted to you guys to be able to compare the main ideas of circuits. Now, this is going to be a project that we're going to be doing over the next couple of days, and probably next week as well. Is we're going to look at the three main parts of what makes a circuit and electricity. Those three main parts, can anyone tell me what one of those main parts that make up like the main things that we talk about when we talk about electricity? Or you can write it down in the chat if you can't. What's the main things that we talk about when we talk about electricity?
Electrons?
Electrons, yeah. Good. That's definitely one of the ideas that we're going to be talking about. Anything else? Oh, someone's saying something in chat because their microphone doesn't work. But I can't see because I've just unrolled my...
Voltage, he said.
Voltage is definitely one of them. Voltage is one. We've got some other, and current is another one. So that was Bao. Thank you, Bao. So yeah, the idea is we're going to be talking about, I'm just going to go back to my pen. We're going to talk about these three things. We're going to talk about voltage, we're going to talk about resistance, and we're going to talk about current. So these are our main ideas here. Okay, let's make a start now on looking at what those different things involve, and how we're going to do that is we're going to start off with this idea here. Now, I think, by the way, as well, if for some reason the Zoom ends early, then what I'll do is I'll just maybe organize a new one, or I'll just record a video and then put it online. What's happening here is we've got this in this guy's hand. A lot of people try to guess what it is. what's in this guy's hand is actually something called amber. Now, amber being like tree sap being crystallized. And of course, in this hand, we've got fir. Now, the main idea here is what people found in like essentially ancient Europe is they found that if you rubbed a piece of amber with fir, you could actually get small twigs, small leaves, different pollen to be attracted to the amber. And they thought it was really weird. And they actually called it electricity. The reason why they called it electricity is because the name amber in Greek is actually electric, which I thought was kind of, I spelled with a K. I know that that's not how you spell electricity, but that's how they would spell it. And I thought that was really interesting because it kind of says, well, this idea of electricity has been a really, really old idea. Now, you guys may have seen these kinds of experiments before where you get a piece of plastic or something, you get some fur, you rub the fur on the plastic, and what happens when you rub the fur on the plastic is all of the electrons, which is exactly what you said at the start, Kevin, all of these electrons actually jump onto the fur.
Oh, it's at the balloon and hair thing, yeah?
Exactly. The balloon in the hair is exactly the same. With the balloon in the hair, I think it's the balloon, the hair. We've got some hair, we've got a balloon. All of the electrons jump from the balloon onto the hair. Now, what happens when you do that? What happens is you end up creating a charge. You end up having this situation where in both of these cases, let's use the balloon in the hair. The balloon is going to end up with losing electrons. So if it's lost, and the hair is going to gain electrons. If the hair gains electrons, it's going to be more negative. And the balloon's going to be a bit more positive. And that's going to mean that it's going to behave a bit interesting. Same idea happens with the rod and the wool. And the same idea happens over here with the amber and the fur. Now, this was great. This type of electricity that they made didn't actually change. It didn't actually move. We actually had a name for that. We called that static electricity. Static meaning stationary, meaning not moving. Stationary, which is not moving. And we've all felt static electricity at some point, whether you've touched the doorknob and you've gotten a zap, whether you've been rubbing your feet on carpet and then you touch something and you get electrocuted. So static electricity is something that a lot of us are pretty familiar with. I actually like this idea of static electricity though. Like ultimately it's not very useful for examining things that every single time you have to rub a piece of amber. What they did is they started to come up with this idea, and I like to show students just because it's a bit interesting for me, a little bit of history. In 1746, several scientists came up with something called a Leyden jar. Now what a Leyden jar is it's just a glass jar. In that glass jar, they have a metal rod that goes down into the jar. And what you could do is you could actually charge up that rod. Some of you guys might be looking at this and say, with that big ball on top, saying it looks a little bit like a Van de Graaff generator. And that would actually be correct. It is pretty much like an old-fashioned Van de Graaff generator. They were able to use this to get a lot of voltage into a small space. And so that was great for them because then they could actually start experimenting with static electricity. They could start experimenting with electricity. You couldn't really do much experimenting with just pieces of amber and fur. So once they found out that they could experiment, what they started to do is they started to look at, well, you know, what's next? The next thing that we found, and this is, yeah, by the way, if you're looking at this and being like, wow, Mr. Greer wrote all this, no, I stole this straight from Wikipedia. I'm not, this isn't designed to be like I want you guys to memorize this. It's just to give you guys some context. So we're moving away from static electricity because essentially Galvani, Louis G. Galvani in 1780, he found that, so this is about 40 years later, found out that he created essentially a battery. I'm not sure if you've heard this story before, but I love this story. He was dissecting a frog. He was using a brass and an iron scalpel. And as he was dissecting this frog, he actually touched the iron and the brass hook near each other. But because they're electrical, they can make a battery, they actually formed a short circuit inside the frog. And that caused the frog to twitch. And of course, he freaked out. I would freak out if I was standing there doing a dissection of a frog and it started to move, even though it didn't have a head anymore. So he actually called it animal electricity because he was like, this is really insane. I don't know what's going on. Is it like evidence of the soul or something? Luckily, he had a friend called Alexander Volta, and you should be able to see now where this is going. And he was like, no, it's probably got to do with something else. And so he invented something called the voltage pile. This here is a voltage pile. And what it was is essentially it was a battery. This is our first battery. Now, this is different to what
That's bigger than AA.
Yeah, it's much bigger than AA. This is much different to what we were talking about before. Here, with the Leyden jar, that's dealing with static electricity. Okay, you build it up and then it goes away. This one was a bit different because it would always make electricity. It never ran out of electricity. It's made from a bunch of copper and zinc discs, and there's some salt water between them, and then that kind of is how they got the battery to work. So now we've got an idea of like current that can be generated, electricity that can be made, and that's sort of what allowed us to then be able to do electricity. Because essentially every time you wanted to use a Leyden jar, you'd have to charge up a rod and put it near the ball and then get the current, and then you'd be done and you'd have to recharge it. Whereas this one was like a Leyden jar that never ran out of electricity, which is pretty good. So what is electricity? Now you'll notice there's a pencil here. You guys, I would like you guys to write this down somewhere. I'm going to leave the, whether it be taking notes on a piece of paper or something else, I'm going to leave this up to you guys. And as well, I'm going to put these slides on Compass in the Classroom so you can write it down. If you haven't got anything with you at the moment to take notes, don't stress, you will get a chance. Plus, I'm recording this session, so when we're done, I'll upload this session so you can like pause it and write it down. So, but essentially it gives us an idea of what the basics is. What is electricity? Electricity is the process in which charged particles. Now, usually when we talk about charged particles, we're going to just talk about electrons because ultimately protons are just too big to move anywhere, right? The whole nucleus just stays in place. But the electrons, they can just move down this wire pretty easily. And the electricity is when charged particles, usually electrons, move from one location to another location. That's what electricity is. When we talk about, electricity going down wires and stuff, all I want you to think about is you're just moving charge from one place to another place. You can even do that through, it doesn't have to be through wires. You can move electricity through other things like through air, through water. That's still electricity. It's just, it's moving charge from one place to another place. So yeah, these notes, I'd like you to take these notes later on, but you don't have to take them right now. And the idea is, hold on a sec, is why do these electrons move? Well, we actually did talk about that just before. If I've got a, balloon, I've got someone's hair, and now the balloon is going to be positively charged and the hair is going to be negatively charged. The reason that the charges will move from one place to another, and this is something that we're going to explore later on, is because ultimately they want to balance out. You want to try and make sure that there is zero charge. So the idea is the negatives will be trying to get attracted to the positives so that there's no charge. Okay, that's why these hairs move up, because they want to get to the positive. They want to try and, cancel it out. That's why when you have a battery, you have a negative terminal. Oh, cool. They gave us some more time. That's why you have a negative terminal and a positive terminal on a battery. Because ultimately, charge wants to go back to the other end because it wants to balance out. So that's why electrons move. I always like to quickly bring that up because often I find there's no point in explaining this stuff if you don't really understand why it's happening. Let me see. Okay, I'm going to talk about one. While I've got you guys here, I might as well talk about these last two slides here. And then that's going to probably be it. Okay, so electric charge. Now, we just talked about how electrons carry charge. So ultimately, how do we measure electric charge? Am I going too fast for people, or are we going okay? Can I get...
No, we're fine. It's all good.
all good?
No one's complaining.
Randomly disconnected, so I am somewhat behind now.
That's all right.
Right,
Thanks,
on you.
Reese, for the thumbs up. That's good.
So could you post this on Classrooms?
Yeah, I'm going to post this after it's done. So if you miss something, I'll put it up.
Just use your photographic memory.
Yeah, and then what we'll do, and then of course, I'm also going to put the slides online as well, so you can access them too. Okay. So
who added the mustache to the picture?
Do
you see the mustache on the picture?
Yeah. I have no idea how you did that. Okay. All right, let's keep going. So what is electric charge? So electric charge is charge is measured in something called coulombs, and it has the symbol Q. Guys, I did not make this shit, so it is a bit weird that even though it's called charge, it has the symbol Q. So this is something that and again, this is a page I would like you to take notes on, maybe not now, maybe later on, but yeah. So charge is measured in coulombs. This is the weird part here. The charge on one electron is actually really, really small. If you think about it, an electron is very, very small. So it makes sense that the charge on the electron is really small. It's 1.6 times 10 to the power of negative 19. That's a really small charge, okay? This is another reason why it's going to be really important that you guys understand scientific notation, because we're going to be using this a fair bit. So here's a question. I'm going to quickly open up the chat because I want to see if someone can say, oh, can anyone tell me what is the charge on 2 electrons if the charge on 1 electron is 1.6 times 10 to the power of negative 19? I've got chat open in case someone can't say. See if you can figure that out. So 3.2 times 10 to the power of negative 19. Thank you, Jason. Yeah, Jason's right. All Jason did, I assume, like is he just went, oh, well, if the charge on 1 is 1.6, I'm just going to go 2 times 1.6 times 10 to the power of negative 19, which is going to be 3.2 times 10 to the power of negative 19 coulombs. That's how much charge is on 1 electron. Okay. Okay. So, yeah. Yeah. This is the beautiful. Thanks to the smiley face too. Cool. All right. So, okay. So then what we're going to do now is we're going to quickly look at the next part, which is how many coulombs of charge would I have if I had 6.2 times 10 to the 23 electrons? This one's a bit of a weirder question. So now instead of saying how many, well, yeah, how would you do this one? So now I've got 6.2 times 10 to 23 electrons. I've got a hell of a lot more electrons. How can I work it out now? I'm going to get chat back up, see if anyone can figure this out. And if you've got audio and you just want to call it out, by all means, just call it out. Okay, here's the question. So, when I had 2 electrons, I went 2 times 1.6. What should I do now that I have 6.2 times 10 to the 23 electrons?
Divide.
5? It's a bit more than 5.
No, divide.
No,
The opposite from multiplication.
you're not going to divide.
I'm here for you, Jess.
Thanks.
I can't get chat open, so you're lucky.
Is
Oh, there it
it
is.
5?
Okay, hold on. No, it's not that, Kevin. That's a little bit too large. I can see what you may be trying to do.
400?
400? No, it's not 400.
I mean, you're wrong. I'm sorry.
Poor, apparently, Brendan Ho. Brendan Ho couldn't get on. That's okay. We'll sort Brendan Ho out later on. Cool. Okay. So I'll explain how to do this one. Oh, here we go. No, Brendan Ho managed to figure it out. Okay. So let me explain how this works. So when I have 2 electrons, I go 2 times 1.6 times 10 to the negative 3. All I've got now, if I had 10 electrons, I go 10 times 1.6. If I've got 100 electrons, I go 100 times 1.6 times 10 to the negative 19. So if I have 6.2 times 10 to 23 electrons, all I'm going to do is go, well, I now have this many electrons, and they each have a charge of this. So what is going to be the charge at the end? How much? Because essentially this is really charge per an electron. So that's what that C per E is, coulombs per electron. So if I multiply those two things together, getting my handy dandy scientific calculator out, 1.6 times 10 to the power of negative 19, timesing that by 6.2 times 10 to the 23, that gives me 99,200 coulombs. Okay, can everyone see why I've done that? Does everyone sort of understand what's going on there? Was everyone a bit confused? Yay, nay. Cool. Anyone in chat confused? Let me just check if I can. No. I think we're okay. Oh, yeah, I think everyone's all right. So that's, if you're a bit confused, please feel free to email me later on. But yeah, the idea is that's how we do it for different amounts. If I said there was 10 times 10 to the power of 3, so 1,000 electrons, you just go 10 to the power of 3 times 1.6. The last idea is here is, well, and this one is one where just your idea that you said before we come into play, how many electrons are present in 1 coulomb? So if I have 1 coulomb, I want to know, well, instead of saying, well, I want to know how many electrons. So I know there's going to be more than 2, but I know there's going to be less than 6.2 times 10 to the 23. So what I've got to say is, well, I have, yeah, I can see that. I have 1 coulomb, and I want to share that 1 coulomb amongst 1.6 times 10 to the negative 19. I want to know how many of these fit into this. And it should be a lot, right? An electron has a very, very small charge. So we should expect to see a lot of electrons fitting in 1 coulomb. If I do 1 divided by 1.6 times 10 to the power of negative 19, I get 6.25 times 10 to the power of 18 electrons. Later on, later on, guys, I want you guys to go back over this and see if you can understand what I sort of did here to figure out that. That if you sort of get this, these two, all I'm doing is I'm multiplying. I know how many coulombs are in our electron. I'm just multiplying the amount of electrons by the coulombs per electron. This one, I now know how many coulombs there are, so I'm just dividing it by the amount of electrons. Yeah, let's jump ahead to, so Andre Ampere is our last sort of topic for today. He was able to sort of look at this new idea called current. And the idea is current is the flow of electric charge and has the symbol I. So this is important. Firstly, it has the symbol I. It's measured in amps or amperes, so A. So this is why it gets confusing. Current, because we've already used charge, current has a symbol I and measured in amps.
Sir, the period has ended.
Yeah, the period ended.
It's ended, and I gotta go to a different for my English
All right.
meeting now.
Oh, thanks for that. Yeah, right. I'll probably talk about this then next time. I'll put this video on. Give me a second. I'll put this video. Let me stop sharing this. I'll put this video on Compass later on. And then what we can do is we can look at that later on. Okay, thanks guys. If you need to get out of here, you can get out of here. That's cool. I will put that on Compass and we'll deal with that later.
Bye, sir.
Thank you so much. Bye.
Okay.
Bye.
See you.
See you, sir.
See you later.
That was a wonderful lesson.
Thanks you. Thank you very much.
Yeah, I only joined like for a bit.
That's all right. The whole thing will be on Google Classroom and Compass. So I'll upload
Yeah,
it.
I was reading the PowerPoint like while you were at it, so
Okay.
should be fun.
Good. All right. Beautiful.
All right.
See you.